Hello everyone, my name is Aisha Akil and I work at Technical University of Munich. It is now around 9:30 p.m. So, but and it's going to be dark soon. But we want to discuss today about Landau's theory of phase transitions, and I will take an example of ferroelectrics. Let's begin with ferroelectrics. What is ferroelectricity? And then I will explain you what Landau did and in his theory of phase transitions. So all these materials you can actually term it as dielectrics, and even water, air, you can write dielectric constant for everything, even metals, but metals will have very large imaginary part. So so in principle, we can ferroelectric is indeed a dielectric material. And then there are some subclasses. They are piezoelectric, pyroelectric, ferroelectrics. The important thing about this, all the circles which are inside, apart from dielectric, just normal dielectric, has to do with the symmetry of the material. It is very interesting that how symmetry plays so important role. So all these other subclasses apart from dielectric actually has no invariant center, which means here is an example. So if you have a point in a crystal which has some lattice coordinates x, y, z, and you apply an inversion operation, meaning that you will change all these points to minus x, minus y, minus z in space, then the material or crystal structure does not stay the same like this. Rabbit has no picture of rabbit has no invariant symmetry. You can think of such an example. So it's not like a cube which you can just which is just symmetric for inversion operation, but it's a system which is which has no invariant center. So all materials, all these special classes, piezoelectric, pyroelectrics, and then ferroelectrics, which I will talk today, are actually materials which has one symmetry element less, so it has no invariant symmetry. So and when we talk about polarization, so what we want to say here, that you have a material and you can polarize it, and this material has no invariant symmetry, then it's a ferroelectric, and we will see some more properties also. Here, by polarization, we simply means that the density of induced electric dipole moments in a dielectric material. Because why dielectric I say here? Because all of these subclasses are indeed dielectrics. So what is special about ferroelectrics, apart from all these, is that it has a spontaneous polarization, and this polarization, it can be reversible if you reverse the direction of the electric field. So the term spontaneous comes from that if you cool down a ferroelectric material and below its ferroelectric transition temperature, it has a net polarization, a non-zero polarization without applying any electric field. So this is called spontaneous. And when you apply an electric field, you do not really call it spontaneous. So spontaneous is a non-zero polarization when you are below the ferroelectric transition temperature. And reversible, this is a hallmark for ferroelectric. So if you are below ferroelectric transition, you can actually get a hysteresis loop. This is what I mean by reversible. So at a certain electric field, all the ferroelectric domains will align along field direction. And if you reverse the field, all the ferroelectric domains will align in the opposite direction. So this is switchable. And one other important thing is that it has a non-zero polarization. If you put the electric field to zero, it will still has some remnant polarization. So this is a hysteresis loop. You may recognize it from ferromagnets also, because they are very similar. Hysteresis loop. There we call it remnant magnetization, but here is remnant polarization. So this was just a very brief introduction what are ferroelectrics, because then we can look into more details in terms of Landau theory of phase transition. So now here is a fictitious crystal. So this crystal is made of opposite atoms with opposite charges, shown with small and big circles with different colors. And but it tells you that above the phase transition, the crystal looks like this. It's a 1D chain. In reality, it's not true. So you do not really have long range order in 1D systems. So it's a fictitious crystal here. And then when you apply and when you cool down the system, hypothetically, at below the phase transition, what happens is you will create dipoles, and depending on the electric field direction, where it can be towards your right side or towards the left side. But the main point is that you create a dipole, and now you can see that the distance between the atoms is slightly different. And now the left side and the right side is not symmetric as above example. So it's just very it's not a true system, but it's just an example that there is no inversion center when a system is becoming ferroelectric. But now, if we look to the free energy of this system, you can, for when the system is centrosymmetric, which means that it's a paraelectric material, there is no net spontaneous polarization. You will get the free energy like a parabolic, like a parabola with minimum around zero polarization. And if you take a thermodynamic system, which is now ferroelectric below transition temperature, and then it has no inversion symmetry, you will get 2 dips in this with plus. It can have positive polarization or negative polarization, and zero polarization is not now the minimum free energy state. So system will prefer below phase transition to be either with plus polarization or minus polarization. Here they are drawn actually with at the equal position, so equally probable in this situation, but in reality it's not like this, because you apply an electric field which will select one minima to be more preferred than the other one. And this situation is actually shown here. So when you apply in one direction electric field, one minima is actually preferred. So let's consider from here, you have all the polarization, all the domains polarized actually in one direction. So this minus B is actually preferred. And as you decrease the field, electric field, you will follow this curve. And when you go to the other direction, all the domains are preferred in the other direction, and the minima will shift to the plus B. So this is just a hysteresis curve, ideally for ferroelectrics. And depending on the grains, you can have even some banana-like hysteresis loops. So this tilting of the potential wells actually happens when you apply an electric field, because there will be a preferred direction. So these potential wells will not have equal energies. One will have lower energy and one will have higher energy. So this example of fictitious crystal is taken actually from this reference. You can follow more details here. This situation is actually when below the phase transition temperature, you will have these situations, and all actually microscopic dipoles do not uniformly switch together in reality, because temperature is raised, the thermal vibrations will also contribute here, and so on and so forth. Now let's coming to the Landau theory of phase transitions. Actually, Landau was a very smart mathematician. What he says is that you can, apart from the constituents of the system, so it doesn't matter whether the crystal is made of specific elements, or it's grown by one chemical transport technique or other growth technique, it does not matter. So he said that what matters is the symmetry. So when you have a phase transition, the system will go above the phase transition. It has more symmetry elements, and if you cool down below the phase transition, it will have a reduction in the symmetry. And the system will go from a disorder to an ordered state. And then this means that a phase transition is somewhere symmetry is broken. Here is an example. So if a paraelectric material will have a cubic subgroup, so it will have also an inversion symmetry into its symmetry elements. And if you go below phase transition, it has another crystal structure, tetragonal, and the inversion symmetry will be broken. Here is an example of barium titanate. So when it's a cubic paraelectric material, this titanium atom is actually centered uniformly. So at the interstitial sites, tiny atoms like titanium can fit in these perovskite type crystal structures. And what happens is when it's ferroelectric, this titanium atom can actually shift and you will get an electric dipole with a certain polarization direction. First important thing about Landau theory of phase transition is that the symmetry gets broken. And then the second thing what he defined was an order parameter. And but he says that there is an order parameter which is 0 above phase transition. So here in the paraelectric phase, there is some order parameter which is 0, and then here is some order parameter which is non-zero. And for ferromagnets, this order parameter is magnetization. And as today we are talking about ferroelectricity, so for ferroelectrics, it's the order parameter is polarization. So this spontaneous polarization is non-zero above phase transition, and there is a spontaneous polarization, finite spontaneous polarization below the phase transition. Now, as I said that Landau was a very smart mathematician. What he did, he just took the free energy of a thermodynamic system, which in this case will be a material which is paraelectric and then becomes ferroelectric below the phase transition. And then he write the free energy, Ginzburg-Landau free energy. Functional. So it's here it's only shown that it's function of temperature, and first term is just temperature dependent, independent of the polarization, and second term is free energy, which is dependent on the polarization. So if you take this free energy, what he did, he just used Taylor expansion and write the free energy like this. Here we only take the odd, here we only take the even powers of the polarization, because free energy does not change sign with the sign change of polarization. So if polarization is plus P or minus P, the free energy does not really change sign from here to here. It just stays positive. So to keep this picture, he used expansion like this. And here these are some constants, alpha, beta, and gamma. To keep things simple, you can actually only first parameter alpha, you can take it as a temperature dependent parameter, where T naught can be just your Curie-wise temperature, and T is the temperature which you are changing. You can write this alpha parameter as a constant, which depends multiplied by a temperature function. So now what's going on is when T is greater than phase transition TC or T naught, you have a parabolic configuration, and then you have these two minimas. When T is below TC, it's ferroelectric. And then this situation is not stable below TC. Actually, this has minimum energy, so this situation is stable. And you can take beta and gamma positive just for simplicity. Here we will see also whether it makes sense or not. Important point here is that if you think how many powers you need to get this situation, so how many powers for this power series or Taylor series you want minimum to have to explain a ferroelectric situation, Then the simple is that, so for using Landau theory for ferroelectrics, you need at least power 4. You need to have these two terms, and then situation to situation you can have further terms, but minimum you need two powers, power, square power and fourth power, because if you have only first term involved, you can only get a parabola. So you must get include this term, second term, to get situation of ferroelectrics with two minima. So, and then one important thing here is that if you add more terms, it actually does not change the number of minimas here. It's just change the nature of the transition, which we will see in a minute. So with this, then expansion is, so how usually we find the suitable situation in equilibrium. The free energy you want to have it minimum, so derivative of the free energy you will equate to 0, and then if you do so, you take derivative of this equation, you will get this, and if you put it equal to 0, you have two situations. One where polarization is 0, which is paraelectric situation, and the other one is where polarization is either positive or negative, two minimas as function of t, and here t is smaller than tc. In some further lectures, we can also actually plot it and see how it looks like. And here is actually the situation. T greater than Tc and T smaller than Tc, you have parabolic function, more flat at T equals to Tc, but below Tc, you get these two minimas. And this is actually for second order phase transitions. If you take the second derivative of free energy, so second derivative of free energy in this case will be dielectric constant. So if you take the second derivative of the first equation, you will just end up with this one. This constant alpha, and alpha is function of temperature. So this situation is just dielectric constant is the inverse of dielectric constant changes linearly above Tc. But important point is that if you look here in the second order phase transition, if you think of the second derivative, which is the second derivative of free energy, is dielectric constant. First derivative of free energy here is the polarization. So the second derivative of free energy get a minima in the inverse, and a discontinuity if you see just derivative, and a minima in the inverse of the dielectric constant. So that's why it's called a second order phase transition. And you can see that order parameter, which is PS. PS here just stands for a spontaneous polarization, and spontaneous polarization is non-zero below Tc, and it's 0 above Tc. So this is how Landau had derived this theory for second order phase transition. So the second order phase transition, it was quite smart. It makes sense that for second order transition, the order parameter continuously increases below Tc. So one can think that it makes sense, but how, when we think a little bit more deep about it, it's very difficult to think that how we can get a first order phase transition from Landau theory. And it was actually just a coincidence, or just he just checked for first order phase transition and it also worked. So we will see in a minute how it works for first order phase transition, but just summarizing before going to first order phase transition, we just summarize the second order phase transition. So you have two situations for the second derivative. So above DC, the second derivative of free energy, which is dielectric constant, it has a discontinuity at near TC, and it has a minima in the inverse. These equations just tell this, and this was observed firstly Roche salt, which where ferroelectricity was first actually discovered. Then it was in potassium compounds. For a very long time people thought that you need these Roche salt type structures for ferroelectricity, but later on they observed in perovskites, which was actually a breakthrough. With this, I would like to go to Landau theory of for first order phase transitions. So we have seen this equation already. So it's just free energy, which is expanded by Taylor expansion. So it was just so in first, when he derived the second order phase transition, he considered that these exponents. So first he considered temperature dependent, but second and third exponent he considered positive. As I told you earlier, that at least you need for second order phase transition, you at least need two alpha and beta minimum. So he considered beta positive, but just to check mathematically, he just thought to take beta negative. And this is how you can actually get first order phase transitions. So what happens here, if you take the temperature dependence and you take beta negative, there can be situations even here you can see in this picture maybe much better. So your transition temperature TC is here. In the second order phase transition or first order phase transition, in both, the order parameter T is actually 0. And below phase transition, you should have a finite order parameter, which is spontaneous polarization. But the difference is that even above, a little bit above TC, you already start to get C2 minima. They are local minima. It's still higher than this one, but you have some local minima in the free energy. However, for second order phase transition, you get these minima only after the phase transition. And when you decrease the temperature further, at some point, these minima are these potential wells or dips are the lowest energy state which system would really prefer. But above TC, there is still some temperature range where you already in the free energy, you can see this this minima. This has consequence on the phase transition, which we are going to see in a minute. But for for the moment, what you can think is that if you if you plot the free energy as function of the polarization, you can already have some minimas which are locally minima above the phase transition. So with this, if you drive this equation further, you can actually take the first derivative, which you will get polarization, and also the second derivative, which will give you again the dielectric constant, and you plot it. You will see, to make it a little short, I will just show you quickly what it is going to give you in the end. You will have actually a sharp change of spontaneous polarization. It's not continuous, it's very sharp. So now the sharp change is actually in the first order, is in the first derivative of free energy. So that's why it's first order phase transition. And the second derivative of free energy, which is dielectric constant, has also changes at the phase transition, but it is not as sharp as spontaneous. It's, as you can see in the spontaneous polarization. And then there is a relation with the inverse of the dielectric constant. What's important here is that there are two temperatures defined, T1, T0, close to TC. And this has to do with this local minima. And then afterwards, you really have this minima, which is globally the minimum state. It has to do with the latent heat. Now, if we look further here, I think you can get a better picture of first order and second order phase transition. So if you look the down, which is second order phase transition, you can see that above transition and below transition, temperature TC, the order parameter is 0, and above is also 0. And if you come from low temperatures to high temperature following this red curve, you will get a trend, and you can call this TH, where the transition happens. And if you follow the blue curve by going from high temperature to low temperature, you can call this transition temperature TC, where the transition is happening. And the difference between these two is delta H, which is a latent heat involved. So depending on from where you are going towards the phase transition, you can have a change in T, which will be a result of latent heat involved. So there is no latent heat involved in the second order phase transition. And you can see a clear change near TC in the second derivative of free energy, which is dielectric constant. And now if we go to first order phase transition, you can follow the red curve, which is if you are going from low temperatures towards high temperature, you will get a phase transition. And if you go from high to low, you will get again a phase transition, but there is a finite delta T involved, and that is latent heat. So depending on from where you are coming or going, you can actually stuck the system into this local minima. So you will already go create a local minima, and you can stuck into it. So there will be a latent heat involved, and that is which you will actually see here also in the dielectric constant, that there is also a latent heat involved. So the main important features, the order parameter increases discontinuously in the first order phase transition, and in the second order, the discontinuity is in the second derivative of the free energy. which is actually the dielectric constant. So an example of this is barium titanate, or PZT is also actually a good example of this. It's also second order ferroelectric. First order ferroelectric, sorry. So here is an example. So material goes from cubic symmetry, and then the symmetry is going lower and lower as you go down in temperature. So it is already ferroelectric here, but then there is some further transitions. And there is latent heat involved. You can see in all of them a hysteresis loop, and you can also see that how the crystal structure is changing, and where the crystal structure is changing, the symmetry elements are also changing. And then these change in symmetry is directly related here to the change of the order parameter. And then you have you can actually see that the change in the spontaneous polarization also happening, because the material symmetry elements are changing. And then again, you can follow similar situation in the dielectric constants. And depending on from where you go, you can have actually a latent heat involved. With this, I would like to finish here. It's quite dark outside, so so I will finish here, and perhaps we'll cover a few of the things which are missing in the next time video. Thank you very much. And so everyone, have a nice time, and thank you.